Hello and welcome everyone. I am Sandipan, and with this video I'm going to introduce our work, GetFair Generalized Fairness Tuning of Classification Models. This is a joint work with Florian Lemmerich from University of Passau and Markus Strohmaier from University of Mannheim. As the title suggests, our work is related to the problem of fair classification. So in particular, we consider the task of binary classification, where each data point belongs to one of the two classes which are represented here by class 1 and class 2, and additionally they also belong to a particular group whose membership is determined by the value of the sensitive attribute. In this particular example, this is x or y. So in this particular setting, you are provided with a training set with all these data points, and what a classifier model will try to do is generate a hyperplane which separates these two classes of data points. So in this particular example, this classifier model seems to have done quite well in differentiating the data points of one class from the other, and that's represented by the accuracy that this model achieves, which is 0.90. But if you look closely, what you will observe is that this model has a higher probability of assigning a class 1 or the blue class to a data point with a sensitive attribute y than, let's say, to a data point with sensitive attribute x. Ideally, for a fair classifier, these two probabilities need to be really close to each other, and in that sense, this particular classifier, which is very accurate, is deemed as unfair. By the way, this differences in probabilities is similar to what is called statistical parity in fair classification literature. Of course, the problem of fair classification is not new, and there are many algorithms which have been designed to enhance fairness of classifier models. So then the question arises that if there are already so many solutions to the problem, what extra are we doing on this? So when we looked into the existing models, what we found out was that often these are specific to a particular classifier model or fairness metric, which means that if a new classifier model is designed or a new fairness metric comes up, then these solutions would not fit. Similarly, most of these algorithms also require the training data in its entirety to enhance fairness. So if there is a setting where the training data is not available or it's proprietary, then again these models are inadequate. And finally, if you want to optimize for multiple fairness metrics, which is often the case, then also there is no particular solution proposed by these methods. So the overall objective of GetFair is to design a tuning framework which allows us to tune the parameters of the classifier model to achieve fairness. So then the immediate question is, can't we just deploy a stochastic gradient descent type tuning approach, which is something like you start with the random initialization of the parameters of the model, and at each step you kind of update it based on the loss. And what you can do perhaps is to replace this loss with the fairness objective, and then it should work, right? But the problem is that these fairness objectives are non-differentiable. So we cannot directly deploy a stochastic gradient descent based method. So what if we could use a similar setup, similar tuning framework, but without needing to differentiate the fairness objective? So as it turns out, this tuning procedure in stochastic gradient descent closely resembles a learning paradigm which is called reinforcement learning, and we look into policy gradient in particular. So in this setting, there is an agent and an environment which is represented by a state at each time point, which is again sampled from a state space. The agent interacts with the environment by taking an action AT, which is again sampled from an action space. The environment reacts to it by moving to another state ST plus 1 and also providing a reward RT as a feedback. The agent selects an action based on a policy pi, which is again parameterized by phi, and the overall goal is to maximize the reward. So we have this reinforcement learning setup and this tuning procedure. So I think you can already guess where I'm going with this. So what we do is we model we use the model parameters as the state of this environment. We design the reward as the fairness metric. And finally, the action determines the direction of the update, which is either -1 or +1. So the tuning formula of stochastic gradient descent boils down to this. So we update it based on the action taken, which is between either -1 or +1. Then you have the learning rate and you have the scaling parameter as well. So we update the parameters based on the action, which is either negative or positive, times the learning rate and times this scalar parameter. As it turns out that the amount of tuning data that you need is much lesser in size than the entire training data. Okay, so let's now go over the entire framework once. So we have the policy, which is pi, which is parameterized by phi. It takes as input the parameter configuration of the classifier model represented by theta t, and based on that it generates action. Now once these actions are generated, the parameter configuration is updated using the updation formula which we discussed in the last slide. Now with this updated parameter configuration, the classifier model is deployed on this tuning dataset, which is represented by dtune, to compute the fairness and the accuracy, and this whole thing is considered as the reward. Now this dtune could be a small subset of the training data or some held out dataset. Once this reward is computed, the updated parameter configuration is again passed on to the policy, which again generates a set of action and so on. The initial parameter configuration or theta 0 is the same as that of the trained model, which has been trained with this performance objective. So this is the model which is with the best accuracy, but not necessarily the best fairness result. Uh, each step generates this tuple, which is the parameter configuration and the reward, and one episode is basically all the steps that the policy goes through. So you have this set of two tuples, and once this episode has been generated, we update the parameters of the policy phi following the reinforced algorithm. The only thing now left is designing the policy. In general, any neural network could be used to design it. We use LSTM and provide some justification why we used it in the paper. In general, you can think of the parameter vector as a sequence which could be used as input to RNN model, in our case which is LSTM, and corresponding to the parameter vector you generate an action vector, and using this action vector you can update the parameter configuration. The first thing to note about our framework is that we directly optimize the parameter configuration of a classifier model, and we are in no way dependent on any specific design principle. So hence it's generalizable across any parameterized classifier model. Same goes for the fairness metric as well. It only requires a fraction of the training data to tune the parameters. So it's specifically applicable to scenarios where the training data is not entirely available. It can also simultaneously optimize for multiple fairness metrics. The only thing you need to specify is how to combine these multiple metrics, and the rest should follow. We evaluated our model across different datasets, classifier models, and fairness metrics, and here is one representative result. On adult dataset, we use the SVM classifier model and statistical parity as the fairness metric. So for adult dataset, each data point represent an individual, and the task is to determine whether the annual income of this individual is greater than or less than 50K. This plot shows the accuracy statistical parity trade-off across different methods. So higher the statistical parity, more fair the results. So we start with the unconstrained one, which is a simple SVM algorithm, and it achieves the highest accuracy and in the same time the lowest fairness results. Then we have the pre-processing algorithms by Kamiran and others, one in-processing algorithm by Zafar and others, and one post-processing algorithm by Hart and others. GetFair actually is able to achieve comparable results even though these methods are metric specific. It provides different accuracy fairness trade-offs. So given a particular accuracy threshold, you can obtain the corresponding fairness result. The results are actually quite consistent across all these data sets, classifier models, and fairness metrics. So to summarize our work, we provide a generalized framework for enhancing fairness of classifier models. So it can be adopted across any parameterized classifier model and fairness metric. We are also looking into potential extensions to other machine learning problems like regression and ranking. This is also particularly suited to scenarios where there is incomplete training data, or you need fairness retuning or optimize for multiple fairness metrics. So I could not show you all the results in this presentation, but we would encourage you to check out our paper. Finally, all the data and the code related to the project are available in this repository. So we would encourage you to check this out as well. Thank you for your attention, and I hope to see at least some of you during the main presentation at the conference. So it's scheduled on 22nd of June between 1800 and 1900 hours Central European time. If you have any particular questions, you can always reach me out at my email address. See you and have a nice day.